Hello again to the last section of chapter 11 and the last section of this course. Applications of Taylor polynomials. We want to approximate functions with Taylor polynomials of different degrees. If the function has a f of x, has a power series, has a Taylor series representation, it looks like this, where n is the nth derivative evaluated of the function evaluated at a, divided by n factorial, x minus a to the nth, is the Taylor series at a. Now, the nth partial sum of the series, denoted by Tn of x, is the nth degree polynomial of f at a, which has this expression, because it's fixed and does not go to infinity, right? So it's known, and it's known. So then it's the ith derivative evaluated a over I factorial, everything the same, it's just that we replace the infinity by n. And then we have to change the index from n to I, or j, or k, whatever you prefer, but it has to be a different letter. So in chapter 3, section 10, we learned this. And this is basically the first degree Taylor polynomial, which is the linearization. If you want to go back to section 10 in chapter 3, you will see explanation for this. This is the line that estimates a function near a point. It's the tangent line. So this is the remainder. In other words, the function, this function, is a sum of the Taylor polynomial at degree n that we are interested in, plus the remainder corresponding to the same n. If you solve this equation for the absolute value, because we're interested in the error, this is also called error, in the absolute value, it could be plus or minus. It's f of x minus the Taylor polynomial for that degree. So of course these have to be the same. If this is degree 3, then of course this is the remainder corresponding to degree 3, Taylor polynomial. Now, one other topic here, and then we can start working on problems, is how to estimate the size of the error, which is this. One possibility will be to compute using a calculator or graph or estimate. That's one possibility, but we are going to look at these two mainly. We are going to graph also, but 2 and 3, let's discuss 2 and 3. If we're talking about an alternating series, then we will estimate the remainder or the error by simply computing the nth plus first term. So this is also presented on page 768 for the alternating series. What do we do if it's not an alternating series? If this is not an alternating series, then we have something called Taylor's inequality theorem, and it's found on page 798. I did not mention these two before because we didn't use them. Now we use them, so we have to go back to them. So in order to estimate the same thing, right, Rn, the error, we have to use this inequality, the Taylor's inequality. So this is clear. If this is 5, will be 6 factorial. This will also be 6. X minus a, it's all clear because a is given to us. And how do we estimate m? So that's the only question here, how to estimate m. We will determine the n plus first derivative and then estimate its upper bound. So what does this mean? So if we're talking about R3, then we're going to differentiate and find the fourth derivative and then try to estimate or come up with a number that is the upper bound of the absolute value of that expression. Okay? And of course, we are given an interval. So we will know exactly where x is going from which number to which number, right? So we will be able to estimate m. Once we have m, and of course we have a, and n is given because if this is 4, then this is 5 and 5 factorial and 5 here. So we will be able to come up with an estimate for the absolute value of the error. Okay, I wrote all these first so I don't spend too much time in writing and you watching me to write. So let's start with problem 7 on page 818. And we're asked to find a Taylor polynomial, and it is T3 of x, which means degree 3, n equals 3. Center the number given to us. So the function is f of x equals natural log x, and a equals 1. So remember, we have first to go back to the Taylor series. So for natural log, so T3 of x will be f of 1 plus f prime of 1 divided by 1 factorial times x minus 1 plus the second derivative of f at 1 over 2 factorial x minus 1 squared plus one more plus the third derivative at 1 divided by 3 factorial, and of course x minus 1 to the third power. So now let's find f of 1, which is 0. Again, f of x is natural log x. So from here we have f prime of x, which is 1 over x, or x to negative 1. F prime of 1 will be 1. The second derivative will be negative x to negative 2. And the second derivative evaluated at 1 will be negative 1. The third derivative of the function will be 2x to negative 3. And the third derivative at 1 will be 2. That's all we need for degree 3. F of 1, f prime of 1, f double prime of 1, and the third derivative at 1. So now let's find T3 of x, which will be, so this is 0, so we jump directly here, putting 1 in front. So we have x minus 1 minus 1/2, right, 2 in the denominator, x minus 1 squared plus 2 over 6, x minus 1 to the third power. And to clean it up a little bit, just here, change this into 1/3. There is nothing else. You don't have to expand. You don't have to do anything else. So this is good enough. Okay. Now, we can also graph. They're asking us to graph f of x and so I have these functions already in there. So we can also graph. They're saying a graph f and T3 on the same screen. Since we are talking about 1, so I'm just going to put in natural log first of all. Natural log x. Then I'm going to put in this long polynomial. Yes, we could have expanded it and cleaned it up and just simplify it, but it's good enough. So x minus 1 and minus 0.5. I will open the parenthesis x minus 1 squared, and then plus, in parentheses, 1/3, and open again x minus 1 to the third power. No, I didn't mean that. To the third power. Okay, so I'm going to use a viewing window between -1 and 1 with a scale. I mean, actually, we can expand that. Let's say -5 to 5 with a scale of 1. And -5, natural log does not exist at -5 anyway, so let me adjust that better. So since I would like to see the y-axis, so I'm just going to put -2 to +5, 8 doesn't matter, y minimum, -5, let's say to +10 with a scale of 2, and let's see how close these two are. As you see, we're interested in 1. So as you see, they're really, so let me zoom in. Maybe I can see it even better, number 2. Okay, so I just need to change the viewing window again to -5, to 5, and y minimum -2 to 4. That would be okay. So obviously, we notice that natural log, which is this function, has a very good approximation using this polynomial around 1. As you see, from this point till this point, they're almost overlapping. I don't know if zooming will show anything better. Not really. I have to adjust the viewing window again to zoom in this particular area. So I'm going to try again 0 to 2. So let's do that. 0 to 2, -1 to 2. 0 to 2, -1 to 2. Okay, let's try that to see even better. I think that that convinces you that indeed the polynomial is a very good approximation of f of x, which is natural log x, near or centered at 1. Okay, moving on. Next problem, problem 9, on the same page, 818. And this time we have f of x equals x e to -2x, and this time is centered at 0. So first of all, we need to determine f of 0, f prime of x, the second derivative. We're asked to find the same thing, t3. So let's start by finding the derivative. So f of 0 is 0, clear, 0 times 1. So let's find f prime of x, e to -2x plus x times -2 e to -2x, which simplifies to e to -2x minus 2x e to -2x. Let's find the second derivative now. -2 e to -2x minus 2 e to -2x minus 2x e to -2x. Let's further simplify it. So we have -2 e to -2x minus -2 e to -2x and plus 4x e to -2x. And of course I can combine these two. So I have -4 e to -2x plus 4x e to -2x. Since it's t3, we have to find the third derivative as well. So let's find the third derivative. I'm going to move on to the next page. Let's see how we are on time. That's still good. Okay, the third derivative. So that will be 8 e to -2x plus 4 e to -2x minus 8x e to -2x. And this is 12 e to -2x minus 8x e to -2x. So we already determined f of 0. Let me write it again here. F prime of 0 is 1. Then f double prime of 0, -4. And the third derivative at 0 is 12. That's all we need before we write Taylor polynomial of degree 3. So t3 is 0 plus 1 over 1 factorial times x minus 4 divided by 2 factorial times x squared plus 12 divided by 3 factorial times x cubed, which happens to be x. 4 divided by 2 is 2, and 12 divided by 6 is also 2. Yes, the question is asking us to do the same thing. Go back and graph. Okay. Okay, I'm going to go directly to this function, clear that, and clear this. So the original function, and again, we were discussing everything near 0. So the function was x e to negative 2x, x e to negative 2x, and Taylor polynomial of degree 3, x minus 2x squared plus 2x cubed, and the viewing window, negative 2 to 2 with a scale of 1, y minimum, negative 4 to maximum 4 with a scale of 1. Let's see what happens. As we already noticed, let's zoom in. Maybe this time will be better. Yes, it is better. As you see, they are almost overlapping in this area near 0. You cannot even say which one is which. Okay, very good. It's a very good approximation. Soon we're going to talk about the error. So let's move on to the next problem. Okay, number 15. And this is still on page 818. And we have f of x equals x to 2/3. They want a equals 1. They also want, they said n equals 3. So again, we are asked to find t3. And we are given the interval for x, 0.8 to 1.2. Okay. So like before, the question is asking approximate f using a degree 3 Taylor polynomial centered at a, at 1, and then use Taylor's inequality to estimate the accuracy. So we're also asked to find R3. So find R3. And what else? And also graph. Okay. So we're going to look at all those. So in part A, we're trying to determine, we're finding the Taylor polynomial of degree 3, first of all. So let's find f of 1. F of 1 is 1. Let's find the first derivative, which is 2/3 x to negative 1/3. And I can put it here, f prime of 1 equals 2/3. Now let's look at the second derivative. The second derivative is negative 2/9 x to negative 4/3. And we can determine f double prime of 1 as negative 2/9. So now the third derivative is 8/27 x to negative 7/3. So the third derivative at 1 will be 8/27. And now we're ready with all this information. We're ready to write t3. So that will be 1 plus 2/3 divided by 1 factorial and x minus 1 plus negative 2/9 over 2 factorial x minus 1 squared and plus one more term for degree 3. So then plus 8/27 divided by 3 factorial and x minus 1 to the third. So let's clean this up a little bit. So we have 1 plus 2/3 x minus 1 minus, when 2 factorial, 2 over negative 2/9, and we flip 1/2. So this will be 1/9 x minus 1 squared. And here this is 6. And when we simplify, we get 4 divided by 81 x minus 1 to the third. Okay. So as we notice, this is the Taylor polynomial degree 3. Let me see how we are on time. So let me stop here. I'm approaching 20 minutes, and I will continue in the next video. Thank you.